Hello. Today, I'm going to continue the discussion of diffusion models. The last lecture was very mathematical and focused on high-level theoretical ideas, which are kind of hard to find in deep learning. And today, we're going to discuss a lot of things that are not so well theoretically understood, but do in fact underlie modern diffusion models. And I'm going to do this in the sense of a timeline. So we're going to go through maybe the last 4 years, which is the era in which diffusion models came to prominence. So I'm going to start with this paper. This is 3 years ago now. Diffusion models beat GANs on image synthesis. So this was the era of big GANs, and they were doing something called class conditional image modeling. So you train a model for dogs, and then you get images of dogs. And this was popular with GANs. And what we're going to be talking about today is tricks for diffusion generation that really improve the quality of the images you see. And the main trick is something called guidance. So, this is the first paper that used guidance. So, class conditional image generation. So we're going to assume a population distribution on XY pairs. And in this case, X is the class of the image Y. And we want a conditional distribution, the probability of the image given its class. So, for example, we want to generate a dog image. We want the probability of an image given the class dog or given the word dog. Now, previous models, GANs, style GAN, trains a model for each class. So it'll train a model for faces, a model for horses, a model for cars. What's going to happen in diffusion models is we're going to train one model that gives you a conditional probability. So it's going to be one model that takes the word dog or the word face or the, whatever, flower as an input, but it's one model, and it's going to try to produce an image for that input. So that's what we're going to do. And this is called a conditional diffusion model, right? Because it's conditioned on, in this case, the class. Ultimately, we're going to condition the images on text, free-form text. But for now, at this time, 3 years ago, they were conditioning just on the class label. So a weakness of GANs is that you have to use a separate model for each X. And it seems to be that a weakness of diffusion models is that you have to use this guidance trick. In principle, theoretically, you should be able to define one conditional model. If you take the universality assumption and you assume your model is infinitely expressive and it can be trained infinitely well, you should be able to get a conditional, an exactly correct conditional probability of image given class, like dog. But that doesn't happen. If you train an unconditional model, even with a diffusion model, you tend to get very poor images if you just do the class conditional model directly. So this paper introduced something called class conditional guidance or classifier guidance. So what we're going to do is we're going to train a classifier. So if you're doing ImageNet, it's very old technology would take in an image and try to produce a label like dog, or maybe the kind of dog, produce a class label for the image. So that is a classifier. So P of X given Y is a classifier for image Y. And we're going to use the classifier to guide the generation of the image. And we're going to focus on doing gradient descent on the negative log probability of the image. So this is guided diffusion image generation. So we're interested here in this equation, I'm using Z for the image. That was the notation that was used in the previous talk. So in this equation, Z is the image and X is the class. And I'm interested in the probability of the image given the class. And I can always use Bayes' rule to say, well, that's the probability of both of them, the image and the class, divided by the probability of the class. This is just a Bayesian way of writing this conditional distribution. And if we're doing image generation, we're given X, right? So it's since the probability of X is a constant, this probability is going to be proportional to this product. So we can do gradient descent on the log probability, or we can optimize our image in diffusion model image generation. We're iteratively improving the image, denoising the image. And what we're going to do is, instead of just going directly for improving the probability of Z given X, the image given the class, we're going to work with this product of probabilities, the prior probability of the image and the probability of the label given the image. So we've got a model of images. Now, this is an unconditional model. This is just the probability of the image. We're going to train an unconditional diffusion model. Okay, so it's just going to have a probability distribution over all the classes, an unconditional diffusion model. And that's this probability of Z. And then we're going to take the probability of Z, but we're going to look at the probability of the class label given Z, and we're going to optimize this product. And because we have a classifier, the classifier is going to produce a probability distribution over the class labels. That's how we do classification. So this is a model we have, a classification model. We can just use that classification model and treat the probability of interest to be the product of the prior probability of the image, that's the diffusion model, and the classifier probability of the class label given the image, that's a classifier model. So then when you're doing diffusion, you're sort of going backward in time. That's what we went over in the last few slides. So we're denoising. So we're taking a noisy image at time t, and we're producing a less noisy image at an earlier time, t minus delta t. We're denoising, so we're going backward in time, and we're going to take a step in the direction of optimizing this probability. So we take the image at time t, or at stage t, and we move in the direction of improving the prior probability of Z, which is also going to depend on T, and plus something that a relative weight, a way of relatively weighting these two terms times the gradient of the log probability of the label given Z. So given a label, we're looking at two things: the probability of the label given the image and the prior probability of the image. And we're going to do gradient descent on the log of this product. And what happens is we've trained a diffusion model for the unconditional probability distribution. And from the last analysis, we have that this gradient, the gradient of the log probability of Z, can be written this way. This is a correct equation from the fancy theory that we used last time. So we're going to take this term and use our U-net, which is trained to produce this quantity. The U-net is going to be trained to produce this numerator. Actually, the U-net is trained to produce this expectation. We know Z. So the U-net is producing this expectation. Now, empirically, it's found that the guidance is very important here. So just to recap, it does not seem to work to simply train a conditional model. It does seem to work to express your optimization function this way as a prior probability on the image and a prior probability of the given label given the image. Now, there's another thing to point out, and that is that as you increase S, as you put more and more weight on this term, you tend to get higher quality images because you're looking for an image that's easily classified, say, as a dog. You're looking for an image that's obviously a dog. And as you look for an image that's obviously a dog, you get a prototypical or very good dog image. However, if you want just the prototypical dog, there might be only a small number of truly prototypical dogs. So the diversity goes down. So you get better quality images, but less diversity. So you're not really modeling the distribution of dog images. You're slanting it to be the prototypical dog. At least that's one interpretation. And this paper 3 years ago had other improvements. There were improvements in the UNet, and these improvements went into DALL-E 2. So DALL-E 2, if you remember, that's where we're going in this timeline. That was the really shocking breakthrough. Okay, the next step in this development is called classifier-free guidance. So the previous one was classifier guidance. So in classifier guidance, we've got an unconditional model of images, a probability model over all images, and we've got a classifier. And we're looking for something that's got a high probability over the probability of all images, and which is clearly classified correctly to be in the class you're trying to model. Here, we're going to get rid of the classifier. So this is classifier-free diffusion guidance. So here we're going to give the classifier guidance uses a classifier. Here we're going to be classifier-free. And this was used in DALL-E. So we're going to train now a conditional model. So in classifier guidance, we had an unconditional model. Now we are going to train a conditional model. But some fraction of the time, we give a null conditioning label. So we might have images for dog, what's the image given that it's a dog? What's the image given that it's a cat? What's the image given that it's a flower? We're going to have a conditional model, but we're also going to have an unconditional model. 5% of the time, we don't give it a class label. We have this null label, which is saying we don't know anything about the class. So we have both a conditional model that can be conditioned on any class, and we have an unconditional model, which is the background probability. And so now what we're going to do is we're going to wait 2 terms. I'm interested in generating an image given a class label. And I'm training a conditional model that actually is going to generate an image given the class label. And as I said, that doesn't tend to work very well. To make that work well, you need a kind of guidance. So what we're going to do is subtract the background probability. What does that mean? So I'm going to subtract the log of the background probability. So this is the prior probability on images. This is the probability of the image given no label. So what this optimization is going to do is it's going to drive the image in a direction that's good for the class label. The probability of the image is going up for the class label, but the prior probability is being driven down. So I'm looking for an unusual image that is high probability under the class label. And there was a story told in this paper about why this makes sense, but the story did not make sense. So the theory of this, I think, is still quite open. But intuitively, you've got something you want. You want the probability of the image given the class to be large, and something you don't want which is that the prior probability of the image is large. So you want to suppress random images, right? You want to suppress random images in favor of images that have a very much higher probability of in the conditional model. And this seems to work quite well. And it works quite well where this S is large. Here, they formulated this with the S being greater than or equal to 1. So if it's equal to 1, this term goes away, and you get the pure conditional model. As it goes to infinity, as it increases to infinity, these two terms are balanced, and that tends to work fairly well. So you can set to get good images, people tend to drive that S to be very large, but it's really just balancing these two terms. And I put a learning rating here, which is another parameter of the model, what step size you take. So you can make this very large and then make this smaller to just balance those two terms. Okay, so getting back to the history. So now we're going to do April of 21, again, about 3 years ago. And this was a super resolution algorithm. So a diffusion-based super resolution algorithm. So in super resolution, you're given a blurry image. Here we've got a blurry image of a boy's face, and we want to get a clear image. So what we're going to do is diffusion-based image generation. So we're going to generate an image based on a diffusion model, but conditioned on the input blurry model. So this is a conditional diffusion model that takes as input the conditioning information a blurry image. Now, if you think about diffusion models are they're generators, right? They're image generators. So you can say they're like artists. Diffusion models are, artists are upset because diffusion models can do art. That's one of the big applications. They can do comic book art, graphic novel art. They can do all kinds of art. So what we're asking this diffusion model to do is to draw a picture of a face that really looks like a face, because this is going to be an artist's rendition of a face, such that that face would produce this blurry image if it was blurred. And it turns out that if the artist produces, the diffusion model can look at this and produce a very realistic face. Here, this is the image produced by the diffusion model, and this is the actual image that was blurred to produce this image. This is the reference. And you can see that they look quite similar, but they're also quite different, right? The information just isn't here to tell you where the teeth are positioned. So, this is just a prototypical fictional account of where the teeth might be positioned. And this is a pretty prototypical face. So we're getting a prototypical person given this blurry image. But anyway, it produces high quality super resolution images. It's not necessarily recovering the information, but it's an artist's rendition of what could be there. Then now this is May 21, we get a paper on cascaded diffusion models. So here we're going to want an Irish setter, and that's going to produce a 32 by 32 image with a diffusion model. So this diffusion model is going to be cheaper, right? It's lower resolution, so it's going to run faster. Then I use a super resolution step to increase the resolution by a factor of 2. And then I can increase the resolution again. So it's a cascade of super resolution algorithms, and that improves the efficiency and probably the image quality also. But again, this is an artist's rendition of a Irish setter. Obviously, it's not recovering. There's no information to start here. This is just a straight diffusion image generation. Okay, so CLIP was introduced about this time. CLIP is very interesting. There's a whole lecture on something called contrastive coding. And I'm doing diffusion models now, and the contrastive coding gets used in diffusion models. So I'm not going to go into a lot of detail about the mathematics of contrastive coding. There is some mathematics. It's information theoretic mathematics here that will be in the lecture on contrastive coding. So what is contrastive coding? So you assume you've got two things. So you've got, say, text, Pepper, the Aussie pup. So that's a description of this image. So you've got text paired with images. And I love abstraction. At an abstract level, you've just got two things paired together, text and image. It might be sound and text. But you've got these two things, text and image. And I'm going to take the text and I'm going to pass it through an encoder. So this is sort of like the encoder in a VAE, but it's encoding the text. And the idea is you want the encoding of the text. So this encoder is going to take the text and produce a vector. So this is text to vector. And another encoder, a different encoder, is going to take the image and produce a vector. And that's the image encoder. And now what you want to do in these vectors is preserve the information in this text that's relevant to this image. And in the image encoder, you want to preserve the information in the image that's relevant to any textual description of the image. And so this image encoder is particularly interesting because it wants to preserve any information that's relevant to the textual description. And the idea is that there's mutual information between the text and the image. Given the text, you know something about the image. Given the image, you know something about the text. That's mutual information. And you'd like these two encoders to preserve the mutual information. So that's done approximately with this technique called contrastive coding. So I take a bunch of images, n images, typically a very large number. So you'll take a batch of pairs, and you'll encode every image in that batch, and you'll encode every text block in that batch. So we get the text for all the different texts in the block. We get an image for all the different images in the block. And then you ask a classifier to take, say, this image and try to decide which text it was associated with. Try to pick out the text that it was actually associated with. And here, we're going to assume that text one is associated with image one. So the actual pairs are the diagonal. These are the true pairs. So you're asking this classifier to pick the text, and it's scrambled. So the classifier doesn't know that the text is not in the first position. It has to classify this and say which text was the image associated with. And another classifier is going to take text and ask which image is it associated with. So this is called contrastive coding, optimizing this problem. So you're coding the text and you're coding the image in such a way that a classifier can tell which image is associated with which text. And there are theorems relating the ability of the classifier to do this to the mutual information between the two views here. So, okay, that's an overview of contrastive coding. What's relevant here is that I've got a vector representing an image and a vector representing text. And the idea is that these two vectors live in the same space. And one thing I didn't mention is that the way this classifier works is it's always going to just base it on, it's going to compute a score. We're going to take a softmax to do classification, and the score is just going to be the inner product of the image vector and the text vector. So these are the same dimension. We're just going to compute their inner product and use that as a score in a softmax to decide which text was associated with this image. And we'll do the same thing in the other direction. So we've got a way of scoring every text image pair. And now we can use that in a diffusion model. There was this paper that appeared in December 21, called GLIDE, and there were two versions of GLIDE. One was a classifier-free guidance version of a form we just went over, and the other was a classifier guidance based on CLIP. So a classifier-free guidance based on CLIP. So here we're going to do classifier-free guidance. And one thing that was an important advance here is that this CLIP is giving us image representations and text representations for arbitrary text. We're no longer doing ImageNet classes. We're doing free-form text. So what we're going to do is we're going to do classifier-free guidance. So if you remember that, we're going to optimize the probability of the image given the text. And we're going to try to suppress the background probability of the unconditional image. That's what classifier-free guidance does. And all we're doing here is we're using this CLIP joint embedding of text and images to give us a model of the image given the text. So we're going to take the probability of the image given the text, the log probability, to be proportional to this product of the text vector and the image vector. So CLIP is, in this case, it's just giving us a way of computing this conditional probability. And we have to retrain CLIP, this joint embedding, to handle noisy images, because the diffusion model is, remember, denoising the images. And it uses upsampling, similar to the super resolution method. Okay, this was the big splash, right? DALL-E 2 came out and everybody was shocked. I often say that, the last decade of deep learning has been more what I call the holy shit era, especially the last 6 or 7 years. The history of machine learning research is that you have these benchmarks and people crawl up the performance, they get the state of the art, the soda on the benchmarks. But in the holy shit era, you look at the images that are produced and you forget the benchmarks, holy shit. So these are images produced by DALL-E 2 in response to text. And it's similar, actually, it wasn't that much of an advance over GLIDE. And this is all work done at Google. But it did have one conceptual advance. I'm going to skip over this figure. This figure is misleading, but it's from the DALL-E 2 paper. Really what's going on in DALL-E 2 is that they reinterpreted the CLIP vectors. So recall that if I've got an image Y, that it has a CLIP embedding. So I'm going to write C sub image, C sub for CLIP, the image embedder for CLIP. This is the CLIP embedding of the image Y. And we're going to take an image, and what we're going to do is we're going to construct a kind of VAE. Now, a variational autoencoder. So there's a lot going on in this course. It's hard to remember what these things are. A variational autoencoder takes something, encodes it, in some latent variable. And it's an autoencoder, so it has an encoder that encodes it into some latent variable, and then it can decode it back into the original. And then to make a generator, you train a prior on the encode on the latent variable, and then you sample the latent variable from the prior, and then do the decoding, and you get a sample of your image. So that's what we're going to do. We're going to train a prior. We're going to think of an encoder, a prior on the encoded latent variable, and a generator that samples from the prior and generates the image. Okay, the encoder is taken to be the clip image encoder, right? So the clip can take an image and it can encode it as a vector. So we're going to take that to be the encoder of an autoencoder. And if you remember VAEs, in principle, if you assume universality, any encoder, for any encoder, there's a perfect prior and decoder that exactly models the distribution. So we're not losing anything in principle by taking some arbitrary encoder, except this encoder has been trained, carefully trained to preserve the information in the image that's relevant to the text, right? It's trying to put it into this joint image text space. But we're going to think of it just as an encoder. So we're going to take it to be the encoder of a VAE. But now the generator is going to have a prior that we generate by sampling from the prior and then decoding what we get when we sample from the prior. Both the prior and the decoder, we're going to let look at the text. So remember, the thing we're trying to do is model image given text. That's what DALL-E does. It models image given text. And there's an optimal prior. And so this generator is conditional. We can make it conditional. It doesn't matter that the encoder is unconditional, right? It's just an encoding of the image. The prior and the decoder, the generator, can both look at the text. So we're going to define a probability distribution over the image encoding given the text. And that's the conditional prior on an autoencoder. And we can also train the decoder conditioned on X. And now there's some fancy stuff in how they model the prior and how they model the decoder. But this was a step in DALL-E 2 that seemed to be very significant. And it's a conceptual step, right? It's replacing the simple inner product of image embedding and text embedding with a VAE model. So now they have to train the prior and the decoder to make this work. So that's a quick overview. It sort of ends 2 years ago, 2.5 years ago. Since then, and hopefully in the course, the next version of this course, I'll talk about stable diffusion, latent diffusion, and some other tricks that have been introduced since then. We will get a chance, I think in the next lecture now, we will get a chance to talk about things relevant to multimodal models like GPT-4o. Multimodal models are all the rage right now, summer 2024. So we'll talk about that next time. Okay, thanks everyone.